All right. Yeah, let's get started.
All right. So hi, everybody. My name is Andrew Young. I'm going to start this off. I'm here today with Shane Cannon and Samir Shende, who are going to help us run through a fairly preliminary, but hopefully very useful tutorial on how to get started with containers on HPC. So I'm going to give you a quick overview for containers. This is going to be Container 101 for folks if you haven't seen it before. If you're familiar, some of this may be some interesting review for you, but Shane will then take it and show you how to build your first Docker container using Docker. We have some Amazon EC2 instances that we've put together already and have booted for you. And you can log in and claim those on a Google Doc related to this link here down below. Shane's then going to show you how to use that container, that same one that you just used, and deploy it on a supercomputer, specifically Cori. And then I'm going to quickly walk through some examples with a similar container runtime called Singularity. We're also going to try to show you some best practices and how this all plays into a larger picture with E4S as well. So with that, I think we will get started here. So, okay, what's a container? Simply put, it's a lightweight collection of executable software that encapsulates everything you need to run some specific single task. This includes everything minus the OS kernel, and it is essentially a Linux utility. And this is because it's an OS level virtualization. Essentially, all the processes, and all the user level software is isolated. And the idea here is to create a portable software ecosystem. Portable is, with some asterisk, of course. A lot of people like to think about these in context of virtual machines. And that's probably not the right way to do it. Think of it as sort of chroot on steroids, if you're familiar with some old Linux and Unix terminology. Most people who have heard of containers or have used containers in the broader ecosystem are familiar with Docker. Docker is the most common container runtime and implementation today. It's available on most, cloud commercial tools, widely available on the hyperscalers. And they're really the first to sort of define some of this and provide a container registry service via Dockerhub. So what does this look like? Essentially, you've got your hardware at your base layer. On top of that, you have your host kernel, and that does not change. You're not booting another kernel, or there isn't a hypervisor within it. But on top of that, you have a container runtime that uses Linux kernel features to basically create an isolated container environment. And you can have multiple container versions along with this. And this includes everything you need to know. I'm still stuck on VPN. Everything you need to know about your tools, libraries, compilers, everything in the application, and everything you need to boot your environment. So how are they used, I guess, traditionally in the cloud or hyperscaler world? And a lot of this is focused on creating a lot of loosely coupled services, if you will, where each service is created as a microservice, if you will, within a container. Think of running a web app, for instance. You may need to have several HTTP servers, 2 backend databases, a container logger, et cetera, et cetera. And scaling is generally achieved through, load balancers and service provisioning. And the idea here from at least the hyperscaler perspective is you try to jam as many of these containers together on a single system to increase utilization. A lot of developers really like this from a DevOps perspective. You're able to have and define the same software environment, whether you're developing, deploying, testing, and you only push the changes that you make from each image version to production while not changing a whole new image, if you will. And the idea here is to develop something that works on your laptop and then can quickly be pushed to production services, or quote unquote the cloud. And a lot of the services have been developed to interact with GitHub and other similar developer code methods that have existed for a while now, and many developers are familiar with. So containers are increasingly common for software management of distributed systems. We have a specific need within the Department of Energy, both from the Office of Science as well as the NNSA perspective, to really support emerging software stacks. And the containers are a really unique and interesting way to do that. it allows us to sort of bring in this DevOps problem in the context of HPC and support new frameworks and services that HPC traditionally has not done a very good job at. It's important to note that our HPC systems, to no surprise to anybody here, are very dissimilar from what the cloud infrastructure workloads, right? So what we really need to do is, formulate and run our bulk synchronous parallel, our BSP or MPI based applications, containerize them, if you will, and ensure that they can scale out to upwards of thousands of nodes. And here it's important to realize performance is paramount. So what do we really care about in terms of container features in HPC today? And a lot of this is what I colloquially call BYOE, bring your own environment. And it's this idea where developers can define exactly what they need to run their task or their application. Package it all up, include all system libraries, how the applications run, how it's built, how it's compiled, down to the nth degree, and have that all encapsulated in an environment which they can then take and run potentially on a supercomputing resource. This ability to compose and define exactly how they want their software environment configured and what modular components they want to bring in is really a key aspect. And this enables sort of, as well, an interesting facet of reproducibility, where we could potentially span multiple different architectures, or I could go back years later and rerun the same container image I have now in the future, and have maybe not a guarantee, but a hope that that could work, rather than sifting through years of Java output files, hoping that I printed out some application version, or I have some idea of what I ran 3 years ago. Portability is really a key aspect, right? The idea that I can build a container image and then move it to different computing systems across multiple different clusters or large-scale supercomputing resources, and potentially take my app and scale it from my laptop, or potentially a cloud instance, as well as a supercomputing resource. And all this works very well with version control integration, integrates with existing tools we're all familiar with, like Git, for instance. And the idea here is we can include not only the container images and the layers that we're going to create, as you'll see in a second, but also the build manifests. And this manifest, also called, as you'll see here soon, a Docker file, essentially, tells you exactly how that image was created. And you can go and inspect those images and figure out what version of my third-party library did I install. Things we can't tolerate or don't want with an HPC, overhead. First and foremost, HPC applications cannot really incur or should not allow significant overhead from containers. We have good news here. We've done a lot of scaling studies over the past several years, and generally I think it's fairly safe for us to say that when you build a container image properly, our container runtimes inject no significant or essentially no overhead when using on an HPC resources. We also traditionally don't care about microservices. I think some of this is starting to change with how we're using Kubernetes, for instance, and trying to figure out how that's going to interact with the broader HPC ecosystem. But generally what we're going to focus on here is the traditional BSP workloads and containerizing those. What we're also not trying to do, at least yet, is on-node partitioning. So the idea here is one container image will map to one host, and you don't have to worry about fighting for resources like you do on the cloud. One of the things we specifically can't tolerate is root operation. And this is really sort of the key differentiating factor between container runtimes that you find, like Docker, for instance, and what you'll see here used in a second in the context of HPC. And that is because it's very easy to assume or allow root level access in an isolated environment like a cloud, which relies on virtual machines underneath the hood and other isolation mechanisms. HPC resources are inherently a shared system. And so we need to make sure users stay as regular users and not allow root level privileges. And there's a lot of other things with commodity networking and provisioning of ports that just don't really apply towards the context of HPC. So it's important to try to define what are similarities or what are the things we should expect from containers, and what are the other things that we really don't care about. So with that, you could imagine Docker's not really a good fit for running our HPC workloads. Again, as I mentioned, the security issue is the biggest stickler, if you will. Docker also doesn't really support good integration within our HPC services. Docker's based on a daemon, a client daemon service model, which doesn't really bode well when you try to scale that up on HPC resources, for instance. The good news is there are several different container options in HPC. The three that you'll find primarily amongst the DOE laboratories are Shifter, Singularity, and Charliecloud. I will say there are many more that exists, and every day I turn around and somebody has a new container runtime. The idea here is that they all take different implementations and approaches to how they work and integrate and different features, but you can just pick a container runtime or let, trust the facility's decision and use what container runtime, HPC container runtime you have at that given facility. And you should be successful in this method. So this is generally good news, and we enjoy this diversity here. So we've got this vision, and I'm going to try to show you how you can, this tutorial will hopefully sort of illuminate some of this. The idea here is we can do software development on our testing on our laptops, create a container build that could then be deployed to a supercomputer, and maybe sort of decrease our development time on our supercomputing resource. It allows our developers to specify how to build not only the app's environment, but the app itself, and how to manage that. We could maybe have multiple different container images that are target different platforms. And one of the things we really are going to try to focus on is interoperability. The ability for me to leverage existing tools, not only from the cloud, but in the context of DOE specific resources across the DOE enterprise. This is something that has not always been so smooth, and I think is getting better every single day here. So, and again, performance matters. We really need to focus on building performant images and then supporting that at scale. So what are we going to talk about in this tutorial here? First, you're going to learn how to build your own Docker container. And then we're going to take that Docker container and we're going to try to run it on Cori with Shifter. We're also going to show you some other things that you may find with Singularity. This is another common runtime that you see across the DOE enterprise, and it's good to understand how to work with and interact with Singularity as well. We're also going to try to show some best practices and illuminate some of the lessons we've learned and some of our code teams have fought hard for, as well as how to potentially leverage the E4S container images and how that plays in with SPAC as well. So if we have time, hopefully we will. So with that, I think it's important to start getting going here. So if you haven't already, please go to this link, and you'll be able to walk through some of these demos directly with us.
That's right. Okay. And yeah, Andrew, if you want to.
So with that, I think I'm going to stop sharing and I'm going to turn it over to Shane.
Okay.
Unless you want me to drive, but I think you're probably better.
Yeah, I'll need it, but yeah. Let me find the right window. Yeah, this is it. Okay, good. That might not be the right one. Are you seeing the full screen or just the tutorial? I mean, just the shell session?
We're seeing your shell.
Okay, let me try again, because that's not quite what I want. Shoot. Okay, hold on just a sec. I'm trying to get this. I might not be able to do it. I know what I'll do. I'll share the two windows. I've done that before, I think.
Split screen, right? Yeah.
Yeah, I was trying to do split screen, but it didn't. I'm not sure if that works with Zoom or not. Okay. So let's do share. I want to make sure I picked up. Okay, this one and this one. Okay, let's see. Okay, I think I picked one right, but I picked one wrong. I have too many. I have too many windows is the problem. Okay, let me see. I apologize for this. I thought I was going to be able to do one. Okay, here it is. This one, and that one. Okay. Now I think I've got it. Okay, so hopefully people are seeing the tutorial material right here. If you haven't already, please open up the link to the Google Doc, and you can use that to both post questions, but also to kind of tag an instance of the AWS EC2 instances that we have. Tag one of those to use for your training. And then also, if you don't already have a nurse login, again, you can go to this link here, use this code, and you can sign up. And I've seen a few have already done it, so it looks like at least it's working. Okay, so now let's jump into the material. Looking at the polls, it looks like you know, there was a mixture of people that were familiar with containers, or and some that were, you know, just getting started, some that were a little more advanced. So apologies if some of this is a little introductory, but it's good to just get everybody on the same page. So we're going to start by going through, you know, these first couple of steps. I'm already logged into an instance here. I've made the font larger, but I've made it so large that I can't even fit stuff in. So let's fix that. I'm going to do this just so I've got a little more room to deal with. Okay, that's better. All right, so we're going to start with this first step. We're going to pull an image down. All right, so I think I'd already done this earlier, so it was pretty fast. What we just did there is we told Docker to go look at a kind of a default registry, one that's provided by Docker called Dockerhub, and then pull this image, and the colon 1804 tells it a specific kind of version tag to use. So that's now pulled down on the node, and I can use Docker images to list the images, and we'll see that Ubuntu 1804 is there. All right. Next step, we're going to start up. So that's an image. We've pulled the image down, but we haven't done anything with it yet. So the next step we're going to do is start up an instance using that container, that image, and here we're going to start it with Docker run, and the -it means an interactive pseudo terminal session. And then again, we've specified the image name and the tag. So one of the first things to note is, you know, I was tutorial user outside the container. Inside the container by default, I'm root, at least with this particular image. So that means I can do kind of the things that you would normally be able to do root, you know, would require root privileges in an operating system. So I can do things like install packages and stuff like that. And I can do an ls, oh, darn, I should have changed this. This was originally written for Ubuntu 14.04, and I forgot LSB release is not in 18.04. So sorry, I forgot to update the docs on that. So you can cat OS release, and you'll see Ubuntu and 18.04. So this is just to demonstrate the OS that we're running in on this AWS instance. Its base instance image is kind of a derivative. It's AWS's own kind of Linux distro. You know, here we are in a container, and we're seeing Ubuntu 18.04. All right, remember to type exit. If you forget to do that, and if you try to type Docker and it says Docker not found, then that probably means you're still in a container. You need to exit out before you can do the next steps. We tried to make sure the documentation makes that clear, but just keep that in mind. All right, so there we used an image that came from an upstream provider, somebody that's kind of maintaining this Ubuntu, you know, base image. Let's now try to create our own image to see what it looks like to do that. So I'm going to start by creating a directory and CDing into that. And let's just do a very basic kind of hello world version of a for containers. So I'm going to make a script called hello. All right, so I've done that. For those that are not used to working at the shell, you might, hopefully you know how to use BI. There might, I think Emacs is all and also maybe installed. There might be some other editors too, like Pico. I don't know if Pico's installed. Yeah, looks like it's not. So I've created this script, and now let's make an image that includes this. So I'm going to create a Docker file. A Docker file is basically a recipe that tells the system how to construct the image. Okay, it's similar to like a make file or something like that. Okay, so I've pasted the contents in. Let's just run through these different kind of primitives that you see in a Docker file. So first is from. This basically tells it what image do I want to kind of use as a starting point for this new image. And you can chain these things all the way down. So you could start with something very simple. You could have another image that might have just a set of tools and some other libraries in it that you use for a lot of different images. And then you can from off of that and have things that are more application specific. So it's very flexible. This next one, label, is you can generally just add labels to an image. This is an optional thing, but one convention is to use maintainer and use that to say who created the image. So I'm just going to update it with my information. You can do the same. And then the rest we're going to do add. You sometimes will also see copy will be used. Either one will work in this particular case. And we're going to say add from outside the container into this new containerized environment. Take that hello script and bring it in and call it bin hello. And so it's important to realize that when you're building an image, you are actually sort of doing a series of container executions, manipulating the contents inside that container, and then you get to some sort of final product. That's kind of what's happening. And each of these steps will generate what's called a layer in the build that generates the final image. Okay, and then last we're going to do run. So these are the two main things you'll use. Add is used to bring content, add or copy is used to bring content from sort of outside the container into the image. And run is used to kind of like run operations inside that environment to kind of transform it. So in this case, we're just going to do something very simple. We're going to make that script executable. All right, so now that we've got our Docker file, we're going to build the image. So you can call it whatever you want. I'm going to call it hello 1.0. And notice this final dot, that's needed to say where should I look for the Docker file. So I'm saying look in the local directory. All right, and it's done. And you can see it kind of runs through all these steps. It says from, which it had already pulled down. If it hadn't, it would pull that image down by default. It's adding this label. The next step and next layer is adding the script and then making this change in permission. So I can do a Docker images now and I'll see my hello 1.0 here. Okay, so let's try running it. And since we put it in bin, it should be on the path and we can just run it as such, right? You could also do that as well. And again, just a reminder, we're still in the container environment. So if I tried to run Docker, it's going to say Docker command not found. So if you see that, it probably means you're still in a container. You should exit out. All right, so that works. The other thing to know is you don't have to do these things interactively. You can also just run it directly. So just to demonstrate that, there's us directly running the command. All right. The next step is if we want to use, this image exists locally on this VM, but we can't get to it from elsewhere. So I will kind of just caution that like the way we're going to do this is create a Docker Hub account. The link is in the documentation right here. And then you would need to do a Docker login and it'll prompt you how to log in. keep in mind, these are shared instances. I mean, these are instances that other people know the passwords to. So you might, if you really are a heavy user of Docker, you're concerned about it, you may not want to do this step. But if you want to practice pushing an image, follow the steps here to create a Docker Hub account, log in, and then do this. I'll go through the steps, but I'm not going to actually log in just so that my credential is not potentially exposed. So whatever username you have, you'll want to put that in this path. Here, what we're doing is we've got to retag it. So right now it's kind of this bare image. If I tried to push this to Docker, even after logging in, it would fail. So instead, I need to prefix it with my namespace, my username, so that I can push it into the right spot. And so after I've done that, this will fail because I haven't logged in, but I'm just going to do this step. You would do that, and see it says it's failing because I haven't logged in, right? If we go over here, you can go to Docker Hub, and if you've already, let's see, I'm just going to quickly sign in. Once you push your image, you should be able to go to your namespace, and you'll see that image show up. So I think this is one that I've done in previous ones. All right, I've pushed different variants over time. Okay, so that's just a quick walkthrough of, we've built an image, we've tested it locally, now we've pushed it to Docker Hub. All right, the next step is I would like people on their own, and we're a little behind on time, but if you haven't already done so, go ahead and start this activity. Let's give everyone maybe 5 or 6 minutes to try to do this. Ignore that little caret there. I'm not sure how that crept in. But here is an MPI program, basic hello world MPI. And then I've given some hints. There's a base image that you can use that already has MPI installed. And to compile an MPI application, you can use this step here. So given what we did in this up here and these hints, that might be enough for you to figure out how to create an image that will work for this application. So let's, I'm going to let people work on that on their own for 5 minutes or so, maybe a little bit longer. If people want to respond in the Zoom chat with how things are going, too fast, too slow, and we can kind of adjust accordingly. And we'll also use this as a chance to answer any questions. Maybe as people, if you've already done up to this point and you are actually participating and doing the hands-on stuff, maybe use the reaction in Zoom to do a thumbs up or something like that, just so we have a feel for where people are. And then let me see if there are any questions too.
I don't see any thus far. If people just want to unmute and ask a question, I think that's fine. We can do this.
Yeah, that's true too. We've done this in sort of broadcast mode before, but if you want to unmute and ask questions, you can.
So Hans asked a question. I joined late. Can I do everything on Corey if I already have an account there?
For the shifter portions, you can. For the Docker build stuff, you cannot. If you have Docker on your laptop and you're already used to using it, you can just do that. Most of these steps should all just work fine. Otherwise, in the tutorial page, there's a link on the main site. Let's see. To a Google Doc, and in that Google Doc, you can claim one of these instances. So we still have lots of instances left if you want to try this out. Also, you can use this place to ask questions as well. All right. Let's see. Give people a few more minutes.
So Shane, do you want to walk through some of the layers a little more? Maybe
Yeah,
give
let's
us
do
a
that.
quick example while people are working.
While people are trying to do this, I'll explain layers. So what the layering does is think of the Docker file sort of like a make file. And the Docker tool is pretty smart in keeping track of the state of things and knowing whether or not it needs to do anything. So let's go through just to show that. I'm going to go through and rebuild that image. Okay, and notice it said using cache, using cache, using cache. So it went super fast, right? Because it basically detected like the contents of this file didn't change, so I didn't need to do anything. I've already run this before, I didn't need to do anything. So it just quickly skips on things. But if I change hello and say, something like that, it will detect that and see it's rerun these commands. So it didn't use a cache version this time, and it didn't and but since that had changed, anything past that point will have to get updated. When we talk about best practices, we'll talk about ways to use this to your advantage. So you can think about things that are volatile and you might put those later, and things that are more fixed you might put towards the beginning. So a lot of times when you're making images, one of the first things you need to do is like maybe you need to install a bunch of libraries or compilers or something like that. You generally have to do those somewhat early anyway so that you can use them in your build process. But putting them as early as possible before you add anything, generally it will make the caching work more effectively. Okay, we're at a little over. I'm probably going to give one more minute or so, and then we'll sort of reveal the answer and talk through that.
Does the Ubuntu 18.04 Docker container have MPI-CC? I think I missed that part.
Does it have a what?
MPI-CC?
Not by default. And so that's why I suggested using this base image here as your base image, because it will already have MPI installed.
Okay, great. Thank you.
Yeah. And unfortunately, I don't think I've pushed. I recently just updated that, and I don't think I don't think I pushed the changes up to the repo like I should have. Let me just look real quick. Oh, there it is. Let's see if I had. Yeah, it still references 1404. I need to push those changes up, but this gives you an idea roughly of how that image was built. It's based off of, in this case, it's 1804 now. Some of the steps changed a little bit because some of the tool package names and stuff like that changed, but this is effectively how that image was built. And this demonstrates how you can sort of create one base image and then use that across different applications. Okay, let's go ahead and do the reveal. All right, so this is what the Docker file could look like. From off of that base image that's mentioned here, add your Hello World app that you cut and pasted this into. And then here we added into this app directory, we CD into it, and then we build the application using MPI-CC. And so I think in the interest of time, well, let me see. I think I've got.
You're fine. Why don't we run through this by hand? I think it's
okay. Important. I already have this in the repo as well. So here, we've got the Docker file. I think it should be up to date. Hello World. Yep, same thing. Hello World.c is just a cut and paste. So let's go ahead and build that. Now I would do it something like Okay, so it's, in this case, I had not already pulled down that base image, so it's doing that now. It's adding in the application. I don't know why it's so slow to do this particular step, but for whatever reason it is. Oh, that's really slow. There it goes. Okay. And I really probably need to update it because I think it's missing some header files or something now, but it's fine. It's just a warning. The application did build correctly. Now let's try running it. Let's start by just doing it kind of interactively. So we're going to do scanon hello MPI. And I can do app hello, or I can do MPI run, you know, whatever scale. And there we go. So this shows that we can kind of locally test things. Now keep in mind, you know, I'm limited to the resources on this VM, which are pretty minimal, I think. I think there's just, 4 cores. So it's not like I can do, you know, in 1,000 and it's going to suddenly go fast, but it just demonstrates that all the pieces are working. All right. Having done that, I can actually, I could push that image up to the Docker Hub as well. And I think I've done that for some previous versions of this that we can actually use in the next step. So any questions on that before we go to the next pieces? Now, keep in mind, we're doing all the Docker builds in this AWS instance because the HPC sites will generally not have Docker available for you to just run, say, on a login node or something like that. We're working on ways to make that possible, or with other tools like Podman, but today it's still somewhat limited. So in this case, we're using this AWS instance, or you could use your laptop as well to build images. That's how I actually do my workflow. Typically, I just use my laptop.
Hey, Shane, you want to just show the Docker images command?
Oh, sure.
Real quick.
Okay. So here, let's see. Right.
Yep.
One other thing you can do is you can do Docker PS to see a list of what containers are running. Didn't show that earlier. Since we've been running things and then exiting, you generally shouldn't see. The ones that you do see running, those are actually used for the shifter demo that we'll do in the next steps. Also, in ours, in some cases, I think, well, I don't think we've been using -rm. It's important to know that when unless you tell it, give it an instruction, Docker will kind of preserve that instance. And if you do a ps-a, you'll actually see the exited instances. And these can build up over time, and so you may have to go and clean things up if you want to do that. One thing as you use Docker, you'll learn is like you have to do some occasional maintenance just to free up space. So if I wanted to, like if I was trying to reclaim some space, I could do something like this. And you'll probably see that it'll complain saying that something's using that. See, because I've got an exited instance that used that image. So I would have to first remove that, and then I can remove the instance. Just a quick little tip there. Okay, so let's go to the next segment. We're gonna now, that was all about Docker, you know, running it locally on your laptop or in something like AWS, or maybe you have a workstation that you have full privileges on and you could put Docker on that. Let's now look at what it looks like to use these on an HPC system. And if you don't want to hassle with getting onto Corey, Shifter is installed locally on this node, so you should be able to do some of the steps locally on the AWS instance. So things like, so just so you know, you can try it there as well. Okay, but I'm going to go, I've already logged into Corey using my own account, and I'm going to just use that for these next set of steps. So if you haven't already, log into Corey. If you've got a tutorial training account, it should give you the ID to log into. And then we're going to start by pulling pulling the image. So like Docker pull, you use Shifter IMG pull to pull down an image for when you're using Shifter. And we'll pull down 1804. Now, what happens with Shifter, and this is different than some of the other container runtimes, is there's kind of a shared image repository for the whole system. And so when I pulled this, somebody had already done this recently, so it already pulled it down. So it didn't need to do anything additional. So that's going to be super fast. You can actually do Shifter images to see a list of all the images on the system. And this will take a little while because there are, lots of images already pulled on Cori. All right. If you had pushed your image earlier, you can try pulling it down. If it's public, you should just be able to pull it down without any problems. If you made it private in Docker Hub, then you'd need to log in. There's instructions on how to do that, but I won't cover it here. Okay, so now let's go into that. And before I do, let's just point out that Cori runs, like most of the Cray systems, uses SUSE Linux as its OS. All right, so we're going to do Shifter image, Shifter -- image Ubuntu 1804 -- okay, and it may not be obvious if there's a subtle difference that the prompt changed, but if we do cat, that's the OS release, and that's another place where I need to update the documentation. If we cat OS release, we'll see now that we're in Ubuntu 1804, just like when we ran Docker earlier. So this is great. If there's certain OSs that have a lot of tools that you already want to use in it, then you can just pull those down and start using those if the SUSE environment is problematic, for example. Okay, again, I exited so that I'm back to the outside the container. So now if I'm back into SUSE land. All right. Let's now try running an interactive job. We're going to use that same Ubuntu image just for demonstration purposes. Okay, so let's talk a little bit about this command. Shifter has integration with Slurm, and we have that configured at nurse. So what we're doing here, some of this is the standard invocation. So salloc, one node. Here we specify what node we want to run on. We're actually choosing a KNL node. You could also do Haswell, just by the way. Q interactive, that's because we have nodes sort of allocated for interactive purposes, and those generally come back really fast. And we'll do a 1 hour time limit. Here's the thing that's specific to Shifter. So there's this extra directive that you can specify what image you want to use. So we've used that here. And what that means is that I can do Shifter bash, and I'm now inside the container, and I didn't have to specify anything additional because I'd specified it as part of the job allocation, right? So, here I am, Cray system with SUSE, but I've got a Ubuntu-based container, running here. All right, and you can also do this in a batch script if you want to try this. Same things. Notice that we're doing this dash image, and unfortunately, I said LSB release, and I'm going to update the docs. I just changed from Ubuntu 1404 to 1804, and I just forgot about the fact that this LSB release is not in there. So probably better to put cat etc.os release or something like that. Just know that this is going to the regular queue. It might take a while to run. You could also do the debug queue here, and it'd be a little bit faster. So if you want to try that, you can. This is just to show what it would look like to use it in a regular batch job, and then you would submit it. I'm not going to do that because it'll take a little while to run through the cycles. Okay, the next thing I want to do is talk about running Mpi Jobs, because I think that's something that people would be more interested in. All right, so let's take, if you previously did the steps to build the MPI-based Hello World in the previous module, and you've pushed that, then we should be able to reuse that, okay? And I've got one that I've done previously, and I've already pulled it down. So I think I called it, it's this one right here. And I'm going to use, actually, I think this one is it too. All right, so we're going to use that and demonstrate running an MPI application. Okay, so I've already pulled it down, so I don't need to do this step. I'm going to go straight to this one. And this. Okay, we'll give it just a minute to get configured. Yeah, and that's true. If you want to just use my image that's already prepped, you can definitely do that. In fact, if you do shifter images, you might see lots of hellos and hello worlds that have been left around that probably should be cleaned up at some point. Okay. All right, so next we are going to run it. And this step that's in the documentation will work. The module piece that's there is actually optional for this particular image, but some older images built with older OSs might have a problem. So adding that module option is kind of a safe thing. So let's just look at what we did here. A couple of points. One is the srun is outside the container. So we've kind of basically said, run this parallel job. The parallel job is shifter. So shifter is going to be the sort of starting point for these. There's this additional argument that we specify for shifter to kind of bring in the right MPI environment into the container. And then we run our application just like we normally would. The other arguments, -n2, -n128, those are standard Slurm arguments for specifying how to run the parallel application. And then one other thing to look at here is, great, it ran, but you might be wondering like, well, is it really doing the right thing? Am I going to get good performance? So I want to just briefly show how we do this for shifter specifically. So I'm going to go into the container. Okay, so I'm inside the container. So we'll see app hello is there. Let's do an LDD on app hello. So we're going to look at the libraries that it's using. And what you'll notice is that for MPI, it's using this right here. That is the Cray optimized MPI library. And that's automatically getting stitched in by shifter. And the way it's doing that is it's modifying the LD library path to add that into, to kind of prefix things. So that's going to get picked up instead of the MPI that's inside the image itself. This does have some trade-offs in terms of reproducibility, because it means that if I run it on different systems, it's a slightly different MPI that's getting invoked. But this is sort of the balancing act for how to get portable kind of containers and still get performant containers. So that's a little behind the scenes on how we're supporting MPI on these. Let's see. Okay, and then the next thing I just wanted to show is we haven't talked at all about volume mounts. Another feature of containers is that you can kind of take a location of a path that's outside the container and map it into your container and expose it. So you use the volume command to do that. We'll just, since we're already in this container, we'll just use it here. Actually, let me just exit back. So I'm going to get all the way back to the login node and just do it from there. So let's make an input directory. I think I did this previously, so it's going to say it already exists. We're going to create a fake file in there. So, I can see this here. If I tried to look at data, on the system, there's no data directory, right? But in my container, when I start that up, I actually have the flexibility to kind of map that into an arbitrary location. So I can do something like this. All right, so now I'm inside the container. And you'll see that data is now visible there, and there's that file that we created. All right, so what's nice about using volume mounts is it allows you to kind of create an abstract way of, in the container, I'll assume that my data is always going to be in /data. And then that way, if I go to different systems and those paths might be different on them, I can still use the volume mount to kind of hide that. And then the application and other things inside the container can kind of look in that standard location. And you can do multiple volume mounts and stuff like that as well. Incidentally, Docker has the same kind of behavior. So you could do things like, like that as well. So very standard kind of behavior. The other container runtimes like Singularity and Charliecloud also support the same kind of feature, although the semantics between them might be a little bit different. If you see shift or command not found, one, make sure you're on Corey. Well, actually, it'll work on both, but also make sure you're not inside a container. So you might need to exit out and then get back to, get back outside the container. So just to show, it's a easy mistake to make. I think we tried to put exits everywhere, but we sometimes miss some. So if I try to type shifter in here, it's going to say command not found. So it just means I'm still in the container. You can be a little bit confusing because it's sort of like being in the matrix. You don't necessarily know if you're in it or out of it. Yeah. Okay, good. I think that was that segment. We're actually doing about right on time. Maybe we'll go ahead and let Andrew. Well, I guess we're a little bit behind. Andrew, do you want to go ahead and start the next segment?
Sure, I can. Yep. Let's take a quick second to just pause here and see if there are any other questions folks have or problems.
Yeah. And I haven't looked at the Huva app to see if anybody's asked anything there as well, or in the question board. Let's see. I'll find the window.
So has anybody been able to, anybody want to volunteer that they were able to run a job on Corey real quick here? A couple hands or. Okay. All right. We've got an interactive job. Well, that's good. That's good to hear.
Yeah. Great. This is a little bit fast paced. We sometimes do this over a little bit longer window, plus doing it remote. It's a little tricky, but if people can keep trying to work through these things after the tutorial as well.
So yeah, feel free to ask questions here. I'll try to keep the chat up. Okay, so now we're going to try to transition, and again, this is really quick, but we're going to move back to the. Helps if we can spell supercomputer. We're going to move back to the AWS instance that you were on, and we're going to try and run you very quickly through an example with Singularity. I think somebody was specifically asking about this. The idea here is we're trying to expose you to a bunch of these different container runtimes that you may find across the DOE as quickly and hopefully painlessly as possible. So Singularity is another HPC container runtime, as I mentioned, and it allows you to run a container on an HPC resource as your regular user. The biggest thing to understand is that Singularity works a little differently in a couple of ways, and it primarily is focused around what's called a SIF, or Singularity Image Format. And it's this open source implementation that basically has a new way of encapsulating container images for specifically for HPC. The idea here is that you build these SIF images potentially from Singularity definition files. So you could have, instead of a Docker file, a separate def file for specific to Singularity. We'll show that quickly, but generally speaking, we recommend folks stick with the Docker images. But you can also, more importantly for this crowd, convert a Docker container into this Singularity image format, and then run that resulting SIF file on a different supercomputing resource. So we're going to show this very quickly on the AWS image. So the idea here is you can pull directly from a container registry. Now, Singularity offers their own container registry and library, but you can also very specifically pull directly from any standard Docker or OCI compliant container registry through the Docker URI format. And then there's also Singularityhub. Some folks have heard of this and used it. You can also just use the shub path if you would like to as well. And the idea here is that the Singularity image format or these CIF files are sort of compressed, read-only, and it allows you to go and run this. So we're going to start directly by building just an example from the library directly. So we're going to do the Singularity build. We're going to call LOL cow because we don't have anything more clever to do. And so if you go and run this command, you can see what happens here. It's going to go and connect and pull down this image from the Singularity library, downloads this, creates the CIF image for you, and then from there we can then run it. Now, there we go, it completes. So I can also run this with a Singularity run lol cow.cif, and uh-oh, what happened? Where did I put it? Oh, helps if I spell. I threw an extra O in there for good measure. Yep, and you can see what the cow decides to say. So more important here is we're also able to pull directly from a Docker, any Docker container, if you will. So we can use the same image that we built that we were using directly, this NERSC Ubuntu MPI command here. So you same sort of command, Singularity Build, and think of this essentially as an import, if you will. So we're gonna call this NERSC Ubuntu .cif, and we're gonna pull from Docker and get this Docker URI here. And so we can see what it's going to do is it's going to connect, it's going to pull each container layer one by one, expand that all into a CIF image, and then create and compress all that into one single CIF file. And the idea with these, so you will get some of these warnings. You can almost always safely ignore those, as there's usually some interesting things that you've got to do in converting to a quote unquote rootless container. But essentially those can all be ignored. As you can see, the layers are unpacked and then it creates a nice CIF file. Now what's interesting about these CIF files is this is just a normal file. I can inspect it as anything else, and I can transfer it. I can put it on a Lustre file system. I can send it to some analyst who wants to run my workload directly, and they can just invoke it from there. So rather interesting. Takes a different approach than Shifter, but actually uses a lot of the same tools and techniques under the hood. So I'm going to also quickly show some folks here how to build from a sort of Singularity recipe or a Singularity definition file. We're going to show this because you may see a lot of stuff that that leverages or uses this, and it's okay. What generally our recommendation is, if at all possible, you should work directly from OCI compliant container images, specifically anything that you could generate from Docker. And this is a perfect example. This tutorial is a perfect example of why you'd want to do that. So you could, generate this CIF file and be able to run this on Singularity, as you're going to see here. But I couldn't then very easily take that and run this, say, on Shifter. So, but it's important to understand, sort of the use cases that you can have here. So we're going to create a very similar example here. I'm going to create this def file, and this has a different format, but you can basically see you can bootstrap directly from Docker. So from this NERSC image, I'm just going to go and echo this command. I'm going to put this in my singularity.def file. Now, in order to build this, you need pseudo privileges. So you need to have, say, your own workstation or the CC2 instance to do this build. Now, luckily, we've enabled, pseudo access. But basically, the command is, instead of build, where I go and do an import, say, from Docker here, I'm going to say build this def file. And this does require root level privileges. So you can see it's going to prompt me for the password. The password, I won't say aloud, but everybody should know it. It's directly in the tutorial if I can type it properly. So here you can see it's going to walk through the steps. It's going to download the blob as I've already requested. It's going to store this and it'll make the additional changes. So Singularity also, while this happens, I'll also mention that Singularity also has a sandbox mode. And this is useful if you want to just quickly tinker with an image or muck around with it before putting all those changes, say, into a def file or into, your Docker file directly. And instead of creating sort of a Singularity CIF file, it is just simply a sandbox or a set of, file system directory structure that has your entire container image in it. Again, this is useful for just kind of quick prototyping and testing. It's often a useful command to see here. So there we go. We could see I built my Ubuntu Singularity image, and then I can also run the same command so you could see I've got this latest Ubuntu mpi.cif, and I can also, let me copy and paste properly, run this in a sandbox mode, and it'll do the same build structure here, which you just saw, and it'll go and build it directly in a sandbox mode. So I think I'll stop there, see if there are any questions. Pull up the chat real quick here to make sure. Yes, the red pill. The Matrix has you. Okay, so hopefully folks are following along here. I can then see, I have this Ubuntu sandbox directory, which now looks like a root file system, and I could, go in and, do whatever I would like to within here. Well, within where I have permissions, obviously. And you can modify that by not by the directory structure, but by doing a Singularity run. So I'm going to start to show you some of these commands here that you may find. So Singularity Shell, this is our first way to sort of quick look around. I can cat OS release. You can see, well, I've stuck to the old 1404 image because I haven't upgraded yet, but the idea here is it could be any image, and you could see I'm now in that and inside this container. Singularity, unless you override it, does give you a Singularity prompt, which sort of helps you realize, oh, hey, I've taken the red pill, if you will, and I'm in my container image. So you can cat OS release. You could go, who am I, right? Is a good question. One that we'll leave for the philosophers. But in this particular session, you can see I am running as my user tutorial in this case. And this is specifically on our AWS instance that we have. So you can also run through this example here, run through the exact same thing, which is building a Hello MPI example, just as we did previously. I think I'm gonna skip this, or rather do this I guess I'll do this really quickly. I wanna be careful of our time. So again, to exit, just type exit here, and I can quickly write this up. I make sure, yep. And then again, we can do the same build directly from this. You could do the exact same thing in Docker, for instance, and then just do a Singularity build, hello mpi.cif, and then do Docker : as we did previously in this example. So we're basically doing the same exact thing as we did with Docker, just using Singularity's def file. Again, this is fun for rapid prototyping, but we recommend sticking with the Docker format, the OCI. So So you could see here, it's running through my scripts, it's gone, it's built, it's done the MPI-CC, it's built my image. And now I can use the Singularity run command, which runs this run script, which in this case is, that hello command. And you could see I have executed, that hello MPI, and you can see it's directly on my node. We also, in this EC2 instance, we have MPI specifically installed outside of the container as well. And this would potentially be how you could run with it, say on a cluster, and I could just do an MPI run or do an salloc and then an MPI run. But pretend you're on a cluster for this contrived example and do a Singularity run hello MPI.sif. And so here you can see we're going to invoke MPI outside of the container, and it's going to start up Singularity and run the executable defined in the hello MPI.sif. So there you go. You can see I did a parallel launch in that case. You can also, just as Shane showed you with srun, for instance, if you have a machine that you're on with Singularity that has srun, you could go and invoke this. This is the case with several of our CTS machines at Sandia, for instance. I think I skipped this really quickly. You can inspect these different container images as well, and kind of see what's in there. You can also inspect, so you can see how did I get to this image. You can also inspect a Docker file. Yep, as well, or anything else, any other image that you have. So that's a very quick and dirty example of how to use Singularity. I think the important thing to focus on is sort of that Singularity run command that we did, and how you can invoke it directly with an MPI run, for instance, as well as the fact that these can all work directly from Docker container images. So focus on Docker or Podman or whatever your build runtime is of choice. Put it in container registry, whether it's using an on-premise container registry. Each site has a different container registry, perhaps using GitLab, for instance, or if it's a public image, you can store it directly, as you can see here with our example, on the docker.io, the Dockerhub container registry. And you can build and run directly that way as well. So I think with that, we'll quickly, well, let me check. Are there any questions here on this stuff with Singularity?
I didn't see any specific ones on that. Oh, but maybe, yeah. Did someone
Let's
have
check the chat. Yes, so, okay, looks like you were commenting about labels and tags.
Yeah.
We can mention tags really quickly. So tags, so this is the image name or the URI, and then this is the tag. In this case, it's 1404. When you're building your own images, so if you don't specify the tag, it'll default to latest, which could be very good and very bad depending on what you're trying to do, right? So you can quickly override, and if you get folks used to just pulling the latest image, you can just override this and update it. We generally recommend adding a tag that is actually useful, whether this is a version of the code that we're deploying or the date in which you built it. Those are all good tags, or the type of machine you're looking to deploy it on. So for the NERSC and Shifter example, you could tag it with Cori and version 1.2.3, right? Yeah, so they're asking about Singularity on Cori. Again, different DOE facilities select different runtimes. And for Cori, for instance, at NERSC, you're going to be using Shifter, not Singularity. This is why, again, we really say focus on using and just building your images, not the Singularity way, but just building it as we showed you in our first example with Docker. And importing, if you find a machine that is using Singularity, import that way with Docker. Yep. There are also, as Shane mentions here, you can find Singularity on Argonne or Oak Ridge or Sandia resources, for instance. So I think with that, I'm going to turn it back to Shane, and we're going to try to walk through a quick couple of examples here on some best practices.
That's right. And then I'll probably also quickly, one of the questions was about, we've talked about MPI, we haven't talked about GPUs. I'll try to quickly just show an example of that as well. Okay, so let me bring up these slides. Okay, just wanted to cover briefly cover a few practices you might want to do, mainly in how you're building Docker images, is what these are mostly centered on. Okay, so, and some of these are specific to HPC, but some of them are for generally kind of general as well. Okay, for the HPC kind of use cases, when you're using the HPC container runtimes, this is not always true, but it's generally the case that the containers are not running you're running the containers as yourself, not as root. So sometimes you'll run across images that were built primarily to run with Docker, and they kind of assume their root, and so they might try to do things inside the container that won't work with these HPC runtimes. So that's one thing to keep in mind. In certain cases, the images may be mounted read-only. That's certainly the case with Shifter. And so that means if you're trying to manipulate, just a second, my headphones about to die. Trying to manipulate the contents of the image at runtime, you might have some issues. Generally, you use volume mounts and use writable places to put anything that needs to change. In some cases, certain volume mount locations may be disallowed. I know that's true with Shifter, and there's currently a limitation in Shifter with being able to mount sort of volume mount on top of a volume mount. We should have that fixed, but I don't think it's out there yet. Okay, so let's talk about some practices when building. First off, we didn't show it. You can build with images using kind of this commit operation. It's like you go create a container, you do stuff in it, and then you commit it. Don't do that. Use a Docker file, because then you've got this recipe of how you got the image into that state. We've only been showing this model anyway, so it should be pretty clear. Next thing is pull from trusted images. So once you discover Docker Hub, you will also discover that there are, I haven't looked recently, but ridiculous number of images out there, and you can't necessarily trust all of them. So generally try to start from trusted sources. If you look in from Docker Hub, things without a prefix, without a kind of a path element before the image name, that means they're kind of blessed in a certain way by Docker Hub. It means they come from very official channels and are well supported. So, certainly start with those if you can. Sometimes there's, there might be other trusted sources as well. But just try to look at where these are coming from just to avoid any kind of injection of, some side attack or something like that. You can use version dependencies. This is sort of about getting reproducible builds and stuff. So if you just are cloning, then just like, if you're doing this locally, you're going to go from the main head or master or whatever, and that could change over time. So you could rebuild that image later and get a different result. So it's good practice to try to use a well-defined branch or tag in your code if you want the builds to be kind of robust. Another is I talked about layers. So there's a side effect of this that the layers kind of build on top of each other, and you'd never actually, if you delete contents in a step from a previous layer, what you're really doing is telling Docker, like, hide these things. And then when it creates the final kind of version of that, it will remove those from being visible, but they're still in the layer. So if you run this kind of steps here, you would get a a layer that has the wget, so it just has this TGZ file in it. You'd have another layer that has the unpack code. You'd have another layer that would have the build itself and the installation. And then you would have a layer that says hide these pieces and this stuff, right? So the size of that image is going to be large as a result. If you chain these things together in one run step, then it's just the kind of final product that kind of gets snapshotted, and that's going to be more efficient. Another one is, this is kind of comes over from the bash world. This is good practice in general if you have scripts or things like that that do these kind of stuff. If you could mute if you're not speaking. There we go. Okay. Sorry. There we go. Here I've separated it with semicolons. What's going to happen here is a step could fail. Let's say this make failed in the middle. Well, because it's semicolons, it'll just keep trugging along. And because that remove step will work at the end, that layer would still be considered like, oh, everything was fine. And it would keep going along in the build process. But actually, there was a fatal flaw in there, right? So it's good practice to chain these together with double ampersands, which basically tells the build that, if any of these sequences break and exit with an error, then you stop. And then that would be caught as an error by the Docker build and it would quit things. And you'd know that there was a problem. This trick is good in shell scripts as well. Okay, and I talked about this before, but order matters. Try to put if you add things from like we're doing here, if anything changes in that directory where I'm doing the build, even a small change, it has to rerun all the steps past that. So generally you want to do these operations as late as possible. So here we've inverted the operation. We're going to do all the package installation first, then we're going to add the source. This way I can keep modifying things here and it will just repeat these last two steps. Whereas in this one, it would have to redo the apt-get update, which, those kind of things can be very slow. Sometimes you might have like a Python requirements file. I'll actually add just the requirements file and pip install from that, and then might have a generic add later just to avoid, just so I can use the caching as much as possible. And then another feature is multi-stage builds. This is really useful for like maybe you need to use compilers and other tools to build the application, but you don't really need those in the final image. This can also be useful if you want to use proprietary tools, but you want an image that you can publicly distribute. So you can't have those tools in the image, but if you use the multi-stage build, you can use it to get around that. So this is what that looks like. It looks very similar, but you'll see there's two froms. There's a from up here and a from down here. We labeled this one as build, and we're going to install our compilers and make, and we're going to build the application. And then in our final layer, we say, this is our run image. You don't actually have to do that as run, but the big difference here is, see, we say copy from build this application, right? So the nice thing is this final image won't have GCC or make in it, so it's going to be more compact. Imagine if that GCC was instead like the Intel compiler, which you wouldn't want in a publicly distributed image. You could use this process to avoid that. Just a few other thoughts. You generally want to avoid really large images. Once you get above 5 gigabytes or so, the time it takes to push layers, to pull layers, to build things can get excessive. So in general, data, any large data, you want to kind of keep that outside the image, and you'll use volume mounts instead to mount those up and make them accessible. It also means that the image is really about the code, and then kind of treat data separately. And then you can also use volume mounts as a way to do prototyping. So one thing I'll do sometimes is I'll have an image that has all my dependencies in it, so I don't have to worry about those, but I might keep my code outside the image while I'm still developing it. I'll just drop into that. So I'm using the container almost like a build environment or a development environment. And then once I have everything working, then I can pull those out and make them part of the image for the final kind of release version, you might say. Okay, so that was a very quick round of the kind of best practices. I think I'm going to stop here because actually talking about using containers as a build environment is a nice segue into our last section to talk a little bit about E4S and SPAC. So Samir, are you, don't have a huge amount of time, but you want to do a quick little tour?
So the extreme scale scientific software stack is a curated SPAC-based software distribution. We have binary build caches for bare metal installs on a number of different platforms, as well as container images that are available on Docker Hub and E4S website of pre-built binaries of the ECST products. You can look at the slides which are there in the AWS image, and we had a tutorial. There's a README file that shows how to use pre-built images, and I have a full image in this AWS instance. We also have a tool called E4S CL, which is a container launcher tool that allows for MPI substitution. So using the mpich ABI, you can then very easily just take the MPI in your application and then replace it with the system MPI. For example, if you were on a cluster that had Intel MPI and you wanted to use Intel MPI with the binary that you created from within the container, it allows you to do that substitution using the E4SCL command. You first say init and give a set of parameters, and then you can say launch and the MPI run command, and then it will replace that MPI. This project can be found on our web page over here. And this is how it looks. There's the E4S container launch tool, and then it figures out which host libraries need to be injected in the image of the container as you launch it. So I'm going to try and show you this in an example. Here is our base image. And I will just go to the Zoltan directory. Now, here I can say Singularity run ecp.simg. This is the Singularity image. I'm running this image. There's a README file that has all these steps. And I'm going to build an example that uses Trilinos. So I have SPAC. And if I say SPAC find, it shows me all the 67 different packages that are available, including Trilinos. So I'm in the Zoltan directory. I can say clean.sh and then compile.sh. Okay, so I can say compile.sh like this. And it's now using MPI from our mpich, and it's building the binary, and it's linking in a whole bunch of these libraries. So if you want to see which libraries it actually uses, I can just look at the LDD output and figure out what libraries there are. Say SPAC load minus our Trilinos, and then I can say LDD Zoltan, and it will show you all the libraries from within the container that are being referenced over here. They're all using mpich. In fact, if you want to see how many there are, you can see that there are 47 libraries. Now, how do I use this with a system MPI, where I could possibly have, say, Intel compilers? And this is the Intel 1 API directory. I can say run e4scl.sh. Let's see what it does. It first sets up Intel compilers in your path so that Intel MPI is used. It will initialize the container launch to say, please use Singularity, please use this image, and use this source.sh as a startup command so I can load modules within my execution in the container. So here I'm saying SPAC load Trilinos and some LD preload commands. And then I can launch it using MPI run, which comes from Intel compilers. And then I'll just delete it. So here is the run e4scl.sh. I'm loading the Intel stack. Here is the MPI run. You can see I'm substituting now. It found that there were 10 libraries and 9 files that needed to be modified. But instead of asking you to do the ugly LD library path and settings, it will do it for you. So you can then just launch this, and it's running the application now, the Zoltan application. What's important is that all the libraries that it needs, the 47 different Trilinos libraries, are coming from the container. And you're using the MPI from, so you're able to substitute MPI and then run it. This is just an example of using a full-featured container over here. What is interesting about this E4S container is that it also has software stacks for many other GPUs. If I just copy that image over to a machine that has a GPU and the AWS instances don't have, I can say Singularity run on this machine, and on this system, I will be able to go ahead and use Intel One API within the image. So if I say set vars and I get all these things, I'm inside the container, and I can go to, now I want to use the GPUs. I'm interested in 3 different GPUs, Intel GPUs, AMD GPUs, and NVIDIA GPUs. And this image has run times for all 3 of those. So let me just start from a mkdir build. I'm going to this directory. I'm going to say cmake ... I'm compiling this Mandelbrot program with the DPC++ compiler from Intel One API. And I'll build it and I'll run it on the Intel GPU. I should also mention that we have support for ROCm and CUDA in the same image. So you can, instead of worrying about getting these runtimes and installing it yourself, you can just go to one single image and run all of these. So here is Mandelbrot example. And you see over here, it could access the Intel Gen 12 LP GPU with the DPC++ program. Here is the output. If I say display Mandelbrot.png, it'll show me what it created. I'm using DCV from AWS to run this. If I am on a different node where I do have support for NVIDIA GPUs or AMD GPUs, I can access those. Here is a HPC, which is in my path. I can say make clean, make, and I'm compiling with HPC now for the AMD GPU over here with the same image. So if I say GPU stream HIP, you can see that now it is able to access the Vega 20 GPU HIP device, which is the MI50 GPU from AMD. And I can go into another directory, say spac find CUDA, or even module find module avail CUDA. We support both modules and this, and I can just say module load CUDA, and then I will have CUDA 11 in my path. Make clean, make, and I have created a build with NVCC here. And if I run this, I can access the A100 GPU. So with the same ECP.SIMG image, I have access to GPUs from 3 different vendors. I have the ability to compile and build programs for Intel, Intel GPUs, as well as AMD and NVIDIA A100. It can access those. Now we also have base images that you can use to create your custom image. So you can cherry pick the packages that you want and not use every big package that we have already installed. So with this, I'll just take any final questions and refer you to this e4s.pdf, and you can go to our webpage at e4s.io And we have videos of the E4S tutorial. You can look at this README file. You can download the image that we are all using here from the AWS AMI. Go to E4S page, go to downloads, either pick this Singularity container right here, and we also have support for Power 9, or just go to AWS and pick this image, and then with your own account, you can launch it. If you would like to try out these images after the tutorial, please send me a note and I can bring up an image for you for the duration that you need. So with this, I'll hand it over back to Andrew and Shane. Thank you for attending our tutorial.
Thanks, Samir. That was great. So I think we're over on time, so I think we're going to wrap it up now. Just final thoughts. If you need anything, let us know. We'll leave the instances up for another hour or so. Also, in the tutorial session that you have, we have a link to join the HPC Container Slack channel. So if you have any questions or want any help there, feel free to meet us offline there as well. So with that, thanks a bunch for attending, and we appreciate your attention. Enjoy the rest of the ECP annual meeting.
Thank you.
Thank you, everyone.